Hi, my name is Phoebe Tang, and I worked on explaining the math behind underwater image processing. So, images taken underwater usually have a blue-green filter and they lack warmer colors such as red and yellow. And here's a processed image, and as we can see, some of the colors missing in the previous one were restored. Now, the question is that what causes this poor quality in images taken underwater and how do we solve it? So there are two main factors of this question. So we can take a look at the waves here, and let me just remind you that the wavelengths of visible light spectrum vary from 4 times 10 to the negative 7th meters, which is violet, to 7 times 10 to the negative 7th meters, which is red. Now, as we can see, the brighter colors have a wider wavelength, which indicates that they travel slower. So they cannot travel as fast as the blue and green lights, which results in them getting absorbed, which causes the image to lack those colors. Now, another factor is that the water particles cause light to distort, which causes the images to be very blurry. Now, this affects images taken underwater more because water molecules are liquid molecules and they clump closer together than air particles. Now, as we can see here, the light source shines into the particle, which distorts its path towards the camera. And light rays cannot travel directly towards the camera. So we need to use all of the variables here, like the angle and the wavelength, the velocity, to calculate the original light path to restore the quality of images. So here are some of the variables we are going to need. So lambda is the wavelength, W is the spectrum, I of X is the input image, E of lambda is the radiance of the light source, in other words, the rate of light emitted, C of lambda is the sensitivity of the sensors, S of lambda, comma X is the surface reflectance. So we know that the I of X, which is the input image, is basically spectrum times light emitted times light reflected off surface times sensitivity of the sensors. The reason why we split it into different functions is that we want to manipulate each one. Now we have our equation for E, which is light emitted as well, and we will need it later on. So let me introduce the gray world assumption. So this theorem is that if I take all the pixel values of an image and average them, it is a shade of gray. Now this is easier for software engineers to calculate and restore colors back to the image if we assume the average is gray and just work from there. Now K is the constant of the exact shade of gray, and we have the equation here. Now it is found that if we substitute K, which is the shade of gray, into the original image function, then we get rid of the weaker light spectrum, and that makes it easier for us to restore the colors. Now we multiply both sides by E here. So as we can see, I replace this with K, and I multiply both sides by E, this side with the variable and this side with the value of E, to simplify this integral right here. And after many simplification, we get this right here. So this function is merely affected by n, and n is a variable we use to control how much we want to modify the light intensity and the path to process the image. So as we can see, we plug in the shade of gray in the original image to eliminate the weaker source of light, and we use n to control how much we want to modify the light intensity. Now it is found from the Minkowski theorem that when n equals to 6, it works best in most cases. Now let's talk about color channels. So there are 3 channels, and every single color is made from those 3 channels. I've listed some of the values for the common colors, so it makes it easier for you guys to understand. So if we put all 0, take all the colors away, it's black. And if we maximum every single one, it is white. So what we do with color channels is we split the image into 3 color channels and we modify each one. So to restore the colors, we, like I said, split the image into 3 color matrices containing pixel values for each point of the image of that channel. And we search for a max and a min value of those pixels. And we go through the matrix again and compare each pixel to the extreme values. We set a buffer for the distance allowed, and if it crosses that buffer, we increase the difference of each pixel and the matrix and the extreme values. So this results in a wider spread distribution of the histogram and less clump of intense values in the middle. And to find this, we take the derivative of the histogram function, which is h prime of I, and this is the sigma notation of it. So basically the equalized histogram is just h prime of the source that you want to equalize. Now I want to talk about Gaussian triangles. So the pyramids measure the pixel position of images, and its dimensions can be calculated with this equation right here. So the reason why we care about this is that the cross correlation operators measure the similarity of 2 matrices, and that normalizes the lighting and the exposure of images. So the cross correlation, the equation for is given right here, and many of you guys might wonder, this equation at the bottom might look similar to this one, and you are correct. So the cross correlation measures the similarity of 2 matrices, and this one right here calculates the angle between 2 vectors. So it measures how much one differs from the other. Now we use the so images are 2D, and we need to modify our cross factor equation to satisfy that condition. So now we just plug in 2 variables instead of 1. And this equation will allow us to find the similarity in color channels, which will allow us to normalize the images to better balance the colors. Now, how do we do all of this? So OpenCV is an open source software library that is very useful in image processing. It is supported for Mac OS, Linux, Windows, and Android, and it provides C++, Python, Java, and MATLAB interfaces. So I have coded my own solution as well. I have linked my GitHub and my results for my project. So I think that everything I talked about involves the software side of solving image processing problems. However, I think we need to look into a little bit more into the hardware side. So I believe that if we install artificial light to the machine underwater, this will reduce light distortion, which will result in less blurry images. Another solution is to install special color filters on the cameras, which will better capture the warmer colors. Now, this is taking a look of the problem from the mechanical side. I believe that both software and mechanical optimization should be used to get the best result of this problem. Thank you.